Hi everyone, and welcome to another episode of Mr. Carlson's Lab. In a previous video, I posed a question to all of you, would you like to see me depot a transformer? And the response to that question was an overwhelming yes, so that's what we're going to do in this video together. And we're going to also design a tool to make this depotting process just a little bit easier. So there's a lot of interesting stuff coming in this video here. So for those of you that haven't seen the previous video, if you'd like to watch that, just below the description, below this video, you'll see a little tab that says Show More. If you click on that Show More tab, the link to the previous video that led up to this one will be under there. You can click on that, and if you'd like, you can watch that after this video or even before this video, whatever makes you happy. In short, what we're going to be doing in this video for all the newcomers here is the transformer itself in that oscilloscope is filled with tar. So what they've done is they've taken a transformer, put it inside of a shell, filled that shell with tar. That shell holds the transformer steady with the tar, and the tar also acts as a little bit of an insulator. Well, what they also did is they potted a capacitor inside there, and that capacitor has gone faulty. And that poses a shock hazard on the case of the oscilloscope because it's basically running from the line cord to the case of the scope. So we need to get rid of that capacitor. In order to do that, we need to depot this transformer, which means that we have to melt the tar in the case of this transformer and pull the actual transformer out of the case. So it's a little bit of a process, and we're going to have to design a tool to do this that will make that process just a little bit easier. Now here's the thing, this transformer is from the late 30s era, and by heating this thing up hot enough to try and melt this tar might also damage the transformer itself. Not a big deal. The oscilloscope will work again no matter what. I have lots and lots of transformers. I can fit another one, even hide it inside that old shell. Not a big deal. We're going to do this in the name of science, so whether the transformer lives or whether it doesn't, not a big deal. We're going to find those capacitors and we'll take a look at what they've actually done in there and how they've potted this thing. What a silly thing to do, put a capacitor in there with a tar. So that's what's going to be in this episode here. So what I'm going to do is get some stuff on the bench behind me here, and we're going to get started in designing that tool that's going to make this just a little bit easier. I removed the transformer from the oscilloscope, and it really came out with ease. 4 screws, 4 nuts, and removing the 4 standoffs. Just desolder the wires, and out the transformer comes. So about 10 minutes worth of disassembly there, including taking the entire scope apart and desoldering the wires. Now you might be saying to yourself, look, the wires are all the same color. This thing's going to be a total pain to put back together. Well, not really. There's a bunch of ways that you can do this. You can ohm out the windings. That's a little bit of a time-consuming process, but it works quite well. If you're unfamiliar with doing that, I'm going to show you guys how to do this here in the near future. We'll take some random transformers and I'll just ohm out some windings and we'll draw a transformer on a piece of paper and I'll show you how to figure out what the transformer does. So that'll be coming in the near future here. A very easy way of marking things is get a bunch of markers just like this, and what you do is when you desolder the windings from wherever they are in the oscilloscope, you can color code the solder just by taking a felt marker and rubbing some of the felt marker on the solder. It really shows up quite nice on that shiny surface. So you can see I've got 2 red wires here, and if I go over here, you can see that this one's blue. So that's blue, and then I've got some green ones marked over here. You can see that's green. Now that all corresponds to what I've marked on the schematic for the windings. So you can see I've got red here. This is a multicolored one. There's green and blue, so I've put 2 stripes on the solder for this. And this is just solid blue and green. And then I have 2 marked black and black that go across the switch. It just is that easy. Now, if the transformer works like this one does, it would be a very good idea to take voltage readings before you want to depot your transformer, because if we depot this thing, there is a chance that heating that tar up hot enough to melt the tar might actually damage the windings. If it does, we want to know how to replace this transformer very easily. So taking some voltage readings off the windings when this thing is on just before you remove the transformer is a very smart thing to do. So you can see that I've got 146 volts AC at this tap here from ground or chassis. This is the tap that runs up to the sweep here. At the top end here, this is the high voltage winding here. We have 402 volts AC. And I have two leads up here that are red and red, which are the filament windings for the 6x5. Now, we really don't need to read the voltage across that because they're attached to a 6x5. The first number in the vacuum tube is the filament voltage, so 6.3 volts. So we know that these are going to be roughly 6.3 volts. Don't need to read that. And same thing with the 913. We have two green wires that run to the filaments of the 913. Not an issue there. You can see that these two wires are black that come out of the transformer. That's because one of the wires that runs into the transformer comes right back out from the outlet again. Kind of bizarre why they did that. Anyways, these two just run straight up to the switch, and it just makes things that much easier to figure out. Now, these capacitors are nowhere in the oscilloscope, so the most logical place for those things to be is inside this transformer. Now, I've had a bunch of people say to me, I'll just get this out of the way here. I've had a bunch of people say to me, Paul, I don't think National would put the capacitors in the transformer. That really does sound like a crazy thing to do. Well, now that the transformer is completely out of the oscilloscope, there's no connection to anything, let's see if we can find a capacitor inside this transformer just by looking at these open windings. I've also had some people say that maybe it's just leakage between windings. Well, let's look for that as well before we depot this transformer. Because if those people are right and there are no capacitors hiding inside this transformer, we're going to depot this thing and risk this transformer for nothing. Now, in the name of science, we're going to do this thing anyways. We're going to heat this thing up until that tar is nice and soft, and we're going to pull it all out. But for the sake of actually knowing if the caps are in here, let's just do a few quick tests and find that out. The first test that I'm going to perform is a leakage resistance test from the windings of the transformer to the case of the transformer. And in order to perform this test, I'm going to use this extremely sensitive leakage tester. So what I'm going to do is take the positive lead of the leakage tester and attach it to the case of the transformer. I'll turn on the leakage tester. Now, the primary winding of this transformer, basically one of the leads just runs right in and right out one of these leads and then back into the transformer again. So what I'm going to do is basically turn the switch on. So I'll just short these two leads here. So this is acting like the switch is closed on the front of the oscilloscope. And by doing that, it attaches both of these leads to the primary winding, so I don't really have to figure out which one is open and which one runs to the winding. So there's such low resistance between these two leads here that I only need to attach the leakage tester just to one of these leads. Again, we're looking for leakage from the winding to the case. So I'll take the sense lead here and attach it to the primary winding. And as you can see, virtually nothing there. Nothing whatsoever. So what I'm going to do is remove this, and we'll test from the case to the high voltage winding here. So I'll click this onto the high voltage winding. And as you can see, just a little bit of capacitance, nothing there. Now, if we look here on the schematic, you can see I have red, red, and this is marked green and blue and blue. You can see that these are all attached to one winding, so we only need to attach the sense lead to one of these wires because this winding is a very low resistance all the way across. So to this machine here, this just looks like a dead short all the way across. So we only need to choose one of these wires, and we've just chosen one of the red wires. So we've completely tested this entire winding for leakage to the actual case right now by just choosing one wire. Same thing with this, because this is such a low resistance here, we only need to choose one green wire. So we'll do that. This here looks like a green wire. It is. You can see the green marking there. No problems. So as you can see, virtually no leakage to the case of the transformer at all. Now, let's test from winding to winding to see if there's any leakage. So we'll test from the primary winding to the filament winding for the 913. So I'll attach this, remove both these leads. I'll attach the positive lead to the primary winding. And we can see that these are green, marked green. So I'll attach this to one of the green leads here. And as you can see, a little bit of capacitance there, not too bad. And as you can see, passes a leakage test, not a big deal. Now, let's see. Now this is where it's going to get tricky. So here's the thing. We've now tested for leakage between the case of the transformer. So you can see that we have a shield in here. We've tested for leakage between the case of the transformer and the windings here. Now, if we have capacitors hiding inside the tar of this transformer, so if one of these capacitors is hiding inside here, you can see that the capacitors both go to a ground. Now, we know that that ground is not the case of the transformer because we've tested from the primary to the case and we see virtually no leakage. Where are they going to attach this? The most sensible place to attach these capacitors would be to this ground right here. So to the blue marked lead running out, because that attaches to the shield. You can see it attaches to a dotted line inside the transformer. So that basically is the ground for this winding here and the shield in the transformer. So, or I should say the common for this winding here. So this is where it's going to get tricky. So what we're going to do is test from the primary to any of these wires on this winding here, and because this is attached, of course, to the shield and all of these, we can choose any of these wires again. So we're to the primary here. Right now we're testing to this, and as you can see, the leakage is nil from this winding. So let's move to this winding here. Look at that. It's looking pretty excessive to me. Now, this is where it gets tricky. In order to determine whether this is leakage from winding to winding, or whether this is a leaky capacitor inside, we need to use a capacitor tester. We need to look for basically capacitance. If this is leaking from winding to winding, this is just going to look like high resistance with almost no capacitance whatsoever. If there is a capacitor inside here and it's leaking, it will show as a capacitor with resistance. So right now we're seeing the resistance. All right, so this is showing quite a bit of leakage. Now what we want to do is look for that capacitor and see if it actually is a capacitor hiding inside there. There are many, many different tests for capacitors. The leakage test is just one of them. So this is a leakage tester, so this is looking for leakage resistance. We have ESR testing. We can test for capacitance. There's all sorts of different types of tests that we can do on capacitors. It just goes on and on and on. Again, this is just leakage, not ESR or anything like that. So what I'm going to do now is remove this tester here. I'll just get this all out of the way, and I'll go get a capacitor tester, and we'll see if we can locate a capacitor inside. Let's look for a capacitor in the transformer with this capacitor tester now. So I'll attach one of the leads from my cap tester here to the primary, and we'll go directly to the ground, so that's the shortest path for this capacitor here. And as you can see, it's confusing this new meter. This isn't all that uncommon. So what I'll do is I'll reverse the leads and see if we can get a reading this way. And because we have windings in the transformer, the meter does not know what to do. Again, quite common. So what I'm going to do is disconnect this meter here, move this out of the way, and connect up my trusty old Tektronix TX3. This thing is an ancient meter and it works awesome. Never given me an ounce of grief, this thing. Here we go. It's on capacitance already. Let's see what happens. 40 nano. So we're looking at 0.04 microfarad. That definitely is no resistance in windings. So there is a capacitor in there somewhere, hiding in amongst the goop. 0.04 microfarad, and again, that's between the primary here and the bottom of the low voltage winding here. So I'm testing between one of these leads. The switch is closed right now, so any of these leads. And this lead right here. And that would make sense because we have two grounds here. They're going to be connecting these two together. 0.04 is hiding in there. So what is the rating on the schematic here? So it says 0.01. So 0.01 and leakage, yeah, it would show up as a 0.04. So there we have it. Yes, National did hide capacitors in the tar. So let's see if we can dig them out or melt them out or whatever. So in order to get the bottom of this transformer off, what I'm going to do is just break these grommets. As you can see, they just pretty much break right off. You can see that how crusty those things are. Look at that. So I've seen them a lot worse. They're like glass. These are just a little bit of flex in these things still. Kind of gummy, I would say. I'll get these out of here like so. That one's like glass. That just breaks off. Maybe this one will be the same. No, not too bad. A little bit gummy. Alright, so I'll lift the bottom of this off now. See if I can wiggle this out. Some of these grommets are still a little bit stuck there. Look at that big tar-filled mess there. Look at that on this side. If you can see that. It's just horrible mess. So this thing is just filled with this horrible sticky substance. So the next step to do would be to make a tool to soften this thing up so that we can just remove the transformer. It doesn't look like the actual core of the transformer is too tight. What I'll do is I will zoom on in here just a bit. And you can see that it doesn't look like it's that incredibly tight against the case. So it looks like they have some piece of cardboard or something in there kind of wedging it. So probably to hold it so that it maybe doesn't buzz or something. You can see a little bit on this side, but it's not, you know, like pressed in. If it was, that'd be horrible to try and pull this thing out. So what I'll probably end up doing is heating this thing up very, very hot, and then this tar will end up melting, and then maybe by just holding the leads and pulling up, we can remove this out of here. Might have to try a bunch of different things. So you never know, even the capacitor might be, let me just get this crap out of the way here. Might even be hiding just stuffed right down in there. Again, there's a lot of tar in this thing, so they may have put that way down in there. These leads are pretty stuck. You can see some tape here. That'd be factory tape that they've joined to the windings here. So I bet you the actual capacitors are probably sitting down in here. Something like that, or maybe even on the other side here. Who knows at this point. Yep, this is going to get messy. In order to melt the tar in this transformer, I figure probably the easiest way to do this would be to use a toaster oven. So here's my plan. I'll get this thing out of the way. Move this over here. So I went to a thrift store, picked up this hideous looking toaster oven, and it's pretty ugly. See if I can back this out here just a little bit. You can see this thing is pretty ugly. I got it for, look, it even has crumbs in it still. The handle's broken off and everything. But here's the thing. The elements work, and there's two elements on the top as well. So here's my plan. Since this has a temperature control here, you know, there's temperature control for the lower elements and for the upper elements. What I'm going to do is take the transformer, and between the two upper elements, what I'm going to do is cut a square hole here, and I'm going to put the transformer down inside that hole, and I can adjust the temperature in the oven to bring this up to the point to where the tar just melts. So I don't need to put on the upper elements. I can only use the lower elements, and it'll get nice and warm, so I won't really overheat the transformer. and I'll be able to pull this thing out quite comfortably. So what I'll do is I'll trace around the transformer here, I'll cut a hole in the top of the oven, and then what I'm going to do is screw this down to the top of the oven as well, and that way when I want to lift the insides out, I have the weight of the oven also helping hold the transformer in. I think it should work out really good, so let's give it a shot and see how well it does work. The transformer is now mounted in the top side of the oven. And how I got the hole so nice and square is I just used the bottom plate off the transformer and traced around this here. And I used that to mount the transformer. Just basically drew around this, centered it in the center of the oven, made sure that it was between the elements somewhere, and that worked out quite well. Now, in an oven like this is the top of the case. Inside there's another heat shield to stop the top of the case from getting extremely hot. And I just used an air cutoff tool for that inside. That's a really rough cut. So I did this first one with a Dremel, and it made a nice clean cut around here. And I wasn't too worried about the inside of the oven. As you can see, in there it's looking pretty rough. So I wanted to cut the hole on the inside just a little bit bigger so the heat would travel up the side of the transformer so that it would heat this just a little bit better. And that's why this is so much larger around the transformer. And as you can see, it's somewhat centered between the two elements there. Now, I don't plan on using these elements. I don't want these elements to come on. I just want to use the bottom elements. And I'll play with the controls on the front here to make sure that only the elements on the bottom come on. If these ones come on, they're a ways away from the transformer. I can maybe almost fit 2 fingers between the element and the transformer, but that's going to really create a hot spot on the side here. And I don't want to do that. So I want this to be a slow process, so there's a good chance that we might be able to save this transformer. So this is almost ready to go. Now, another thing that I did notice about this transformer here is they've put a cardboard shield all the way around the entire inside, and they filled the tar on the inside of the cardboard. So it is pretty stuck in there. I used 2 screwdrivers and I tried to lift this out, and it won't lift out. You can see the layer of tar here. I'll just zoom on in. So you can see that there's that cardboard kind of isolating the entire transformer, and that's also what's creating isolation between the core and the case here. And you can see that they very carefully poured the tar within that cardboard shield. Now, I don't know on the top side whether the cardboard is open or not. I imagine it's probably covered. But also, I imagine some tar has gone on the inside of the transformer here as well. Again, I put a screwdriver on this side and a screwdriver on this side, and I tried to lift this out, and it's pretty solid in there. So softening up the tar will definitely make this easier to come out, even if this is a little cardboard box that they've put this thing in. Who knows, they may have even put some tar on the upside before they put the cardboard box in just to hold everything in nice and tight. It is pretty tight in here, and as you can see, there's a pretty thick layer of tar on here as well. I don't know if you can see how thick that is. So the next step is to heat this thing up and see if we can pull this out. So what I'll do is I'll tie all of these wires together like so, and I'll use this just to give a slight tug on this. I'm not going to pull too hard because I don't want to pull the wires out of the transformer. And if this doesn't work, then what I'll do is I'll put 2 small screwdrivers in here and try and ease this out. And if that doesn't work, I'll be carving some of the tar away here, and I'll see if I can maybe get a plier on the core and pull the core out that way. So the wires seems like the easiest way. If the tar gets soft, this might just pull out nice and easy. We'll give that a shot first. Here I'm in the great outdoors with the oven on a workmate bench. I want to do this outdoors because this could get kind of smoky, and I don't know what's in this tar. If there is, any kind of a toxic material in this tar, I definitely don't want to be inhaling this. So it might take a while for this oven to slowly heat up this transformer enough to make the tar soft and melt. So what I'm going to do is I'm going to get that process underway. I'll let the thing warm here for a while. I imagine it's going to probably take a while, and I'm going to want to fiddle with the controls in order to make sure that it doesn't overheat. Again, we want to try and save this transformer, right? So when the tar is nice and soft and melted and I'm ready to pull this out of here, I'll be back. Okay, so this has been on for about 30 seconds, and already this is getting extremely hot. So what I'm going to do is just shut the oven off. I'm going to see if I can get this up. Oh, look at that, eh? little bit of a tug there. Nice thing about the oven is it'll hold the heat. It looks like the actual core is of the transformer itself is there's nothing really holding it together other than that. Oh, here it comes. There it is. Yes, and there's definitely some tar down in the bottom there. So it came out just like this. So what I'm going to do is get this off to the side. It is in a nice little box, and they did put some tar on the bottom here. I'll show you that in just a moment here. I'll move this off to the side. And you can see down in there, you can see the tar right at the bottom. This whole corner is filled with tar down here. See that very clearly. So that's what was really holding the thing in. Yeah, almost no time at all, and this came out, and this thing is really hot. So that worked out extremely well. So now back to the lab. So here's the transformer out of the case, and it's in a nice little box, so there really wasn't a whole lot of tar holding this in. And even that little puddle at the bottom only made slight contact here, so softening the tar up just basically made this soft enough so that the box could just easily come out. It's very nice that they didn't pot this directly into that case, because if they did, I'd had to heat this up quite a bit more and risk really damaging the transformer. So really, this didn't get all that hot, so there's a good chance that we may be able to save this, and that's may be able to. So what I'm going to do now is just remove the cardboard box. I'll have to make a new cardboard box. Again, I really don't want to heat this thing up more than I have to, so the first thing that we're going to experiment with is just getting rid of this box. So this bottom piece here just looks like it's a flap, like that. And here, starting to see the actual transformer. See that in there? So, and look what I see. Right there and right there. So let's just open this up. Maybe I don't have to completely remove all of this. Look what we're seeing. Maybe I can just work this out of the tar and really be careful. There you go. What are you thinking, National? Like, I mean, that was just silly. There it is, right there. And if that's not enough, tubular condenser. Wow. So what I'm going to do is I'm going to just clip these capacitors out and try and get rid of the leads, or just isolate them if I can. And then what I can do is work on just repairing these old leads. What I'll probably do is just slip some new tubing over the old leads, and that way that's probably the most, I should say, least invasive way of working on this transformer. Now I know that the line cord wires are pretty short here, so what I'm going to do is I'll just get rid of these things. We'll take a look at these things here in just a little bit. Look at that, they're even filled with wax. So this transformer got really, really hot, you know, like crazy. I don't know what they were thinking. At any rate, so that's what I'm going to do. I'll get the capacitors out and I'll work on either replacing these leads or maybe even just trying to put some new heat shrink on them. I'll get this underway and I'll be back. Here's a question that people often ask me. They say, Paul, is there any way I can test a capacitor for leakage just using a standard ohm meter? And the answer to that is no, you need a dedicated leakage tester. Capacitors have many different tests, and a leakage test is just one of the many tests. You can see that this meter here goes to 500 megohms. Right now, I have the meter across this capacitor right here. So this lead runs over to here, and there's a little open solder joint over here that I'm just attached to. So this is between these two leads right now, and it's not seeing any resistance, even with this at 500 megohms. Yet, if I switch this to capacitance, this capacitor is rated at 0.01 microfarad. So if I switch this to capacitance and I adjust the range here to microfarad, you can see that it's reading 0.019. So this is rated at 0.01. You might look at this and say, oh, well, it reads 0.01, it's okay. Well, the truth is, this capacitor is horribly leaky. We just haven't tested it for leakage yet. So I'll remove this from the clips here, and I'll just show you the rating of this capacitor. You can see right there, it's rated at 0.01 microfarad at 400 volts DC. So if I move this out of the way, just shut that off, and I'll grab a dedicated leakage tester. So this is designed to test capacitors for leakage. So what I'll do is I'll clip this lead here, again to the same area, and to the capacitor. Now this should very quickly go down to green, and then this should illuminate green, indicating an OK capacitor. So I'll just turn the lights off here. I'll turn this on to discharge. So on discharge, it's not looking at the capacitor yet. So right now it's just acting as it's trying to discharge the cap. So what I'll do now is I'll click this onto test. And as you can see, the light stays red, and it's right at the top of the scale. So this is incredibly leaky. So what I'll do now is I'll remove this capacitor, and I'll take a brand new capacitor of the same value. All right, so I'll just turn this onto discharge, and then shut the unit off. I'll attach a brand new capacitor. Put this down here. Turn that on to discharge, and now we'll test this. So now you'll see this max out, and it should very quickly drop off. That capacitor is absolutely fine. So I'll just click this onto discharge again, and we'll do that test one more time. Light's kind of shining on the scale here. So you can see that. No problems, whereas the other one just stays right at the top of the scale. So this is a dedicated leakage tester. All the plans and the circuit board layout, the schematics and the parts lists, everything is available on Patreon for this if you want to build one of these things yourself. So the replacement for this, if you wanted to test these capacitors for leakage with an older tester, I'll grab that tester now and set that up on the bench, and we'll take a look at that. This is an older style capacitor tester that uses high voltage to test capacitors for leakage. If you ever plan on owning a device like this, I strongly suggest that you do the research, read the manual, and get familiar with the device. If you're uncomfortable around working with high voltages, this is definitely not the machine for you. This thing will source up to 600 volts across these test clips or at these jacks right here. So if you click this into the leakage position, wherever this little pointer is pointing, that's the voltage it's sourcing at the test clips. So if I advance this to say 6 volts, there's 6 volts across that. And as you can see, I can advance this all the way to 600 volts. This jack is not, or this little switch here, is not spring-loaded, so it will stay in the leakage position. You need to manually click this to discharge the capacitor and remove all the voltage across these clips. So if you ever purchase a tester like this, be extremely careful around this. So how this tester works is this puts voltage across the capacitor, and this is looking for excessive leakage current. This eye tube up here will display that excessive leakage current by a closed shadow angle. Right now, the shadow angle is open. And as I advance the voltage control here, you'll see it briefly close for a moment as it's charging the capacitor. When the eye stays closed at the bottom here, we know that we've hit the voltage where this capacitor is excessively leaky. So what I'll do now is I'll click this into the leakage position, and I'll advance this slowly until we hit a voltage to where that eye stays closed. So here we go. 6 volts, no problem. 10, okay. 15's fine. We're at 25. And as you can see, at 50 volts, the shadow angle stays closed, indicating that this capacitor is excessively leaky at 50 volts. Now, this capacitor is rated for 400 volts, and it's leaking at 50, so we know that it's extremely faulty. Since these things are attached to the line cord and then to the chassis of the scope, this makes the chassis of the scope live and very, very dangerous. And these were hidden inside this transformer here. So when I replace those capacitors, I'm obviously not going to put the new ones inside the transformer. They will be external to the transformer. So if you recall earlier, when we tested the capacitor with this meter right here, we tested for resistance. This was well beyond 500 megohms, so that test didn't show us anything. We tested it for capacitance with this meter as well, and it read 0.019. So if we look at the capacitor, its rating is 0.01, so that could trick us into thinking, oh, maybe the capacitor is good. Again, there are many, many different tests for capacitors, and this is just another test. So we have ESR, we have leakage, we have capacitance, and the list goes on, all sorts of different tests. So if you want a safer alternative to testing these capacitors where you don't have to use high voltage, this is definitely the device right here. So this is an extremely sensitive device, and it even has a forecasting feature to forecast future failures in capacitors. Again, all the plans and everything is available on Patreon, and you can build one of these things for yourself for very cheap. Much, much cheaper than these things are going for nowadays, I can tell you that. The transformer is now reassembled and ready to go back in the scope. So I took the time to put new insulation on the wires that come out of the transformer, just to make things a little bit safer, and it looks a whole lot better as well. I put new rubber grommets in the bottom plate of the transformer here, so these are nice and soft now. I replaced the cardboard box that was around the transformer, so that's all replaced. The transformer is held in this box and it's isolated from the actual case of the box. There's a little bit of space between the bottom cap here and the actual transformer itself. You can see there's a little bit of depth in there. So I took a rubber grommet, a large rubber grommet, and cut it right in half, and I put that between this bottom plate and the transformer, so that holds the transformer tight in the case. You might be able to see the rubber grommet inside that hole there. So I lined up the hole of the rubber grommet with this hole here. That worked out very well. Now, when I put the bottom cap back on this thing, they originally had some little rivets that held this bottom cap on, and I would say the rivets that I found and put back in are identical to what I took out. And the whole trick behind that is, when you buy a hole punch, you usually get an eyelet kit with it. And they look like this. And it comes with a little crimper like this. And basically what you do is you just take these things and put them right through and crimp this. Now, I had to modify this. I had to cut this almost flat with this. This has quite an extrusion that comes out around here. So I had to cut this right down close so I could get this close to the transformer. As you can see that it hits the transformer, right? So that worked out very well. This looks completely stock, and that holds the bottom cap on really nice. So if you're ever depotting a transformer, the eyelet kit that comes with a punch works extremely well. And as you can see, I can do a lot more transformers with this. A 632 screw will fit quite comfortably through those holes. So that worked out really, really nice. So the transformer is ready to go back into the scope. I'll get this back into the scope, and I'll put the brand new capacitors in that scope as well. Now there's nothing inside this box except a transformer, the way it should have been in the first place. I'll also have to elongate these wires just a little bit, probably about this long, so this will go to the terminal tie strip where I'm going to put those safety caps. So the caps that were removed were replaced by these, or will be replaced by these, And these are a standard safety cap. So this is an X1 Y2 rated cap. So that replaces these ones here that have been removed. Now you can see the paper is coming off of this. This is another interesting thing I discovered. This got really loose, so I slid this off, and for some odd reason, they just put a paper shell over something that already has writing on it. So you can see here, the cap says outside foil. So they don't have a microfarad rating on this or a volts DC. They just took the time to put that on this shell. Why they didn't print it right on this capacitor, I have no idea. So under these shells, this one is still pretty stuck on this one here. So underneath these shells is basically just a standard Sprague capacitor. So paper and foil style capacitor. So those are definitely going in the garbage. So these will be installed on that terminal tie strip outside the transformer where everything is very easily serviceable. And the terminal tie strip is right below that large filter capacitor that we installed in the previous video. So that'll be done next when I have the transformer back in and we're ready to try the scope out, make sure everything works. I'll be back. For those that are interested, before I put the transformer back in, we'll perform a leakage test to the same area that showed excessive leakage before. So if you recall, these capacitors here are tied from this point here to the blue line here. You can see the grounds are tied together there. So I'll test the same area, so from one of the sides of the primary to the ground of this secondary high voltage winding here, and we'll see if we have any leakage. So I'll do the same thing I did before. I'll just close the switch. So I'll just join these two wires right here. Just like that. So now I can test either one of these wires. It'll go through the primary winding. And we can choose any one of these leads on the secondary side. We'll go right to that ground lead. So technically the capacitors would have gone right across this line from each one of these right over to this ground here. So I'll clip this onto here. It doesn't matter, sense lead or positive to either one. Just like so. I'll turn this on. Good stuff, no problems. Let's see what happens from this winding to the case. Just remove this here. Absolutely nothing from the primary side to the case. And let's test from the secondary side to the case. No problems. Everything is looking great. And this one isolated winding to the case, absolutely nothing. So the transformer is looking good. The power transformer is installed in the unit, and I've also added a fuse holder and a fuse. So you can see I've installed these two capacitors that were inside the transformer here on this terminal tie strip, and I'm using these tie points to tie the line cord into the transformer. Now, whenever you're installing one of these safety capacitors, if there's going to be a side that's going to be closer to the chassis, obviously this would be the side that you would want to tie, because you can see that this side runs over to this side of the capacitor. So it's just a little bit of added protection. So to say that this was close to a grounded surface like a chassis, you can see that this, if it's tied to the actual chassis, would be a more sensible idea than, of course, having this side here tied to the chassis and then this tied to the line, because you could get very close to the chassis with the line cord. Just something to keep in mind when you're using these safety capacitors. That was taken into consideration when these were installed here. So this is just about ready to go back in the case. All of these wires are what links the bottom portion of this scope into the upper portion of the scope. Once I have it all back together, we'll do a leakage test between the line cord and the case of this, and then we'll fire it up and see if we get a trace on the screen. The scope is all back together. Let's perform a leakage test from the line cord to the chassis. So this here is ground. I don't know if you can see that there in the camera. This little post here is ground. I have it a little bit darker so that we can see the display on this just a little bit better. So what I'll do is I'll take the positive lead of the tester and just clip it to the ground. It really doesn't matter which order this is in. And I'll just select one side of the line cord here. Click this on, just like that. Get that out of the way. Turn this on, and let's test for leakage. Looks good. Now the moment of truth. Let's see if the scope lives. So what I'm going to do is plug this into my isolation transformer and variac supply. And I'll turn this on. Just get the light off the CRT here. You can see that a little bit better. Let this warm up for a moment. Oh, I see a trace. There it is. Looks great. Project successful. Thanks for stopping by the lab today. I hope you enjoyed this video involving the depotting of this transformer. If you did enjoy the video, you can let me know by giving me a big thumbs up and hang around. There'll be many more videos coming like this in the near future. We'll be taking a look at a lot of very interesting antique and modern electronic devices together. If you're interested in taking your electronics knowledge to the next level and learning electronics in a very different and effective way, you might want to check out my Patreon page. I'll have that link just below the description, and I'll also pin that link at the top of the comments section as well. So you can click on that, it'll take you right there. If you do go, check out the community section. There are a lot of people sharing their ideas and projects there as well. All right, until next time, take care. Bye for now.